Hi guys, in this video I'm going to talk about offline reinforcement learning and how is it going to change the whole RL paradigm. And then I'm going to talk about the model-based offline RL and a method that I have developed, and we'll discuss how it's going to be beneficial and which situation is better to use that. So without further ado, let's jump right into it. Welcome everyone to the channel, AI Fun Fact for All. For those of you who are new to this channel, my name is Pedro Morgan. I have a PhD in computer science, and in this channel, we talk about AI and machine learning and how we can use it in order to maximize our efficiency. As I mentioned, in this video, I first want to talk about offline RL and what's the difference between an active setting and an offline setting. We'll also see that what makes RL to not see a lot of attention and how this offline RL can actually change that, and we'll see what are the benefits of this offline RL. And then we'll discuss going into a model-based offline RL and how we can use it in some setting, and then we'll talk about the method that I've developed, MoReBRAC. We can see that MoReBRAC optimization in offline setting, so we want to have an advanced decision-making systems with uncertainty. So the problem definition is that we're gonna have some online interaction, or we're gonna have some distribution match, or we're gonna have some real-world application. So we know that in reinforcement learning setting, we need to have access to the environment to do the trial and error, but there are so many cases due to the safety or some other cases this is not available. We want to have access to the real world environment. We cannot do anything that you want, and then there's also a lot of discrepancy between something that you see in the simulation and something that happens in real world. So basically there are some constraints that happens in so many different domains such as transportation, and how we can actually use it given real world data. Right now we see that there's a lot of attention on the real world data, and we see that you can have a lot of interaction, can actually use them. So one might say that let's do imitation learning, or basically mimicking the behavior in a supervised manner, but we know that it's gonna fail in some adversarial situation, which means that let's say in a autonomous driving situation, you are not going to see lots of edge cases or lots of scenarios, and since if you're doing only imitation learning, then your agent wouldn't be able to do if there is some adversarial case. For example, a child come into front of the for example vehicle, or there's a cone on the side of the vehicle, so it doesn't know what to do, and then real world application actually lacks high quality data. So then if it is not high quality, then the imitation learning is not going to be good. The other approach is obviously reinforcement learning. Now the problem is reinforcement learning is that there is a generalization gap. So supervised learning can learn from massive amount of data like internet, but RL is, as we mentioned, is a closed world environment. So in order to have a generalizable method, you require both of these components, the massive amount of data and also very high capacity model. So basically this is impossible in active learning settings such as like on policy or off policy setting. So what we need to do then, that's where the offline RL come into play. We mentioned vendor exploration is limited, for example medical scenario, real world cases, or there are hard generalizability required. For example, we want to have sim to real or adversarial or safety. And now we want to know that how we can use this pre-connected data as a starting point to then later on do some fine-tuning with RL. How we can learn the best policy possible and do it for different trajectories. Here is an example. The optimal path, there are like, let's say we have 3 paths, and these are the demonstration that we're given. The optimal path is this black dots. Obviously it's going like directly from the first point to the end point. This is not available, and it's very hard to learn that. If we do behavior cloning, this basically means that we are learning an average of what we have seen in the data. So that's going to be the purple one. But can we do something better than that? Because that's definitely far away from our optimal one. It is obvious that we can do something like the red, which is very close to the optimal. So the optimal one might be learned with an RL if you have a scenario that you can do lots of interaction. And so RL suffers from, RL can learn basically the good stuff from the mix of good and bad. So as we can see, it's not in an average like a BC would. There is some generalization, which means that some good behavior in somewhere can suggest good behaviors in others. As you can see in here, we can see, let's say, for example, we can skip some node, and that's what we did in here, and there's some stitching, so you basically can stitch one part and then connect it to the other part. So some good behavior from here and good behavior from there, and then we can stitch it together. RL there suffers from out of distribution. So that basically means that we want to explore and we demand some counterfactual, and worse than that, we want to also maximize those values, because as we're going, we get to the question of what if we take this action, and then it is going to be like adversarial learning, because we are learning something that we don't have enough information of, and then in the basically Bellman equation we are going to maximize the Q. So basically we see the over estimation in the Q values. So common solution is that we constrain the policy and we will remain to the behavior one, but this is kind of in contradiction with our case, which is we want to do better than the average. There's other ways that people do it, like re-weighting samples. It can induce some artificial data sets that has probably a higher return. So let's talk about our method, or MoReBRAC. So MoReBRAC, as the name suggests, is a combination of more and the MoReBRAC framework. I'm not going to go into detail of these two methods. The link of them are available in the description, and then we can take a look. But basically, we are going to combine the online learning from the MoReBRAC and also the model-based hybrid method from More, and combine them together to get the best result. So we have what we need to do is that it's kind of like a pipeline. There's two stages. The first is the simulated training, which we train our LSTM GRU and also the VAE model, and then after that we're going to have restrictive exploration, and we're going to do some data augmentation. We have some policy update, and finally we can evaluate our simulator. So if we want to go deeper into what's the approach look like, we have a prioritized augmented replay buffer, which means that this is augmented because we are going to ask the data generated from the simulated plus the data that we have from offline both together, and we're going to make it prioritized, which means that if some of the trajectory have a higher return or lower return than the some quantile, we are going to keep them separately so we don't forget them. And then we have restrictive exploration, which means that we have a sensitivity, elbow loss, and Monte Carlo deviation, and we create a uncertainty loss, and then we're going to truncate or penalize the rebar. Basically means that we truncate the trajectory if the UL is too large, and otherwise we're going to penalize the rebar based on the UL that we have. And finally, on the TDT plus BC, we're going to use a MoReBRAC method for offline fine-tuning. Here you can see some result on four different cases, like random, medium, expert, and full replay. We have the different methods: TD3, BC, IQL, More, SAG, and MoReBRAC, and finally MoReBRAC. And we can see on a random and full replay, we actually provide the best result. These are when the cases where we don't have lots of good quality data. If you have good quality data, basically the TD3 plus BC or the BC itself would be the best one. Here is some evaluation. We remove some of these methods that we have, and it actually provides that the results will not get better if we remove the components. Let's talk about the benefits. If we have this simulator, we can use them for validation, which means that we can test before deployment. We can use it for hyperparameter tuning. We can use it for alias swapping and so on. Right now, people actually try to use the gym itself for validation, but they don't close it. So they just use it for demonstration. They don't technically use it for anything else. But since we have a simulator, we can actually use that. And then generalizability. The model can capture the sparse rebar transition and penalize the rebar and try to generate more samples on the regions that we don't have enough data on. And then we can reduce conservatism by enhancing the knowledge of the agent in some region that we don't have enough information of. Because if you're given the offline data, that's all you're stick with. But if you also have the ability to do some on-policy data collection, that would enrich the data. But you need to basically make sure that you are not doing the naive basically Q learning. Obviously there's still some limitation, which is it requires some reverse signal. So obviously in the beginning we still need to have some reverse signal for our offline data. The complicated structure due to the sparse simulator package and optimizer steps. So we have the complicated structure is exhibit conservatism is high reward. If you have a high quality data set, it will still create some conservatism, and because of the reward penalization and also all of the boundary that we have. And model divergence over long horizon or overfit to behavior policies. So there are some in the future direction if we can detect the quality of the data set, and then we try not to penalize reward on those regions, not to generate more data on those regions, that would be optimally the best result. And there you have it, guys. If you went over model-based offline RL we talk about what is often, how is it different from a conventional reinforcement learning, and then we talk about MoReBRAC. We discuss the ways to actually augment the data from a simulator that we generated in-house and how we can actually use it to avoid over-conservatism and also at the same time not reaching the estimation of the Q values. We talk about the limitation and also future work on what we can do to further improve this result. I've put the link of the code in the description, and also I have a plan to distribute basically a PDF of it as well. I will put the link on the description of the video so you look at it whenever it's become available. You can also take a look at it. I'm also open to discuss. You can discuss in the GitHub or directly comment me on this video or basically my email. Thanks for watching and see you until the next one.